Hello and welcome back. We are discussing section 2.2, Techniques of Differentiation. The second video, we're going to try to tackle this second learning objective, find relative and percentage rates of change. So, percentage rate of change is like a regular old rate of change, like we computed in the previous section. Finding an average rate of change essentially just figured out the slope between 2 points on some graph. And then we had this movement toward the derivative, an instantaneous rate of change, that is, the rate of change at a point. And then a modification of this, instead of just telling me how much, say, growth national product grew by, then we could also say by what percentage did it grow, so a relative rate of change, if you will. So percentage rate of change, to give ourselves a definition, basically looks like the rate of change, so the derivative, divided by the actual output of the function. So this is the slope divided by the height of the graph, essentially. And then times 100 just so we get, instead of a decimal, we get something that's a percentage. And so this is supposed to be the rate of change as a percent of the actual output. So instead of, for instance, gross national product growing by some number of billions of dollars, we could say it grew by 2% or something. Okay, so we're going to revisit an example. If you don't remember this one, that's fine. But in a prior section, we looked at the percentage rate of, we looked at the rate of change in demand for rice, and now we're going to try to turn that into a percentage rate of change. So this is demand in millions of tons as a function of the price, the unit price of rice in dollars per ton. And in the previous section, what we did with this was use just the definition of the derivative to figure out this rate of change in this function. And that was pretty cumbersome because it involved all the conjugates with square roots and whatnot. So we're going to try to make use of our shortcut rules in this case. So percentage rate of change, just taking the definition back again. There is some cosmetic change here. Instead of the function being named f, it's named d for demand. And instead of the input being our generic x, we've named it p for price. But other than that, this is just the definition of percentage rate of change we were given. We're supposed to figure this out at a unit price of 500, so replacing the p-values with 500, we get that. But it turns out that we really want to get a derivative function first. Before we plug in that 500, we want to know what d prime of p is, just this general thing. And the reason for that is we've got all these great shortcuts that help us tackle this as long as we're just looking for the derivative function in general. So here's our set of instructions. Notice it isn't ddx anymore because our input variable is now named p. So now it's ddp. That's just because, again, we renamed this guy. So before we actually get anywhere derivative-wise, maybe some algebraic rewriting would be helpful. This does not look like our variable, p, to some power yet. So our power rule is not going to be super useful with it written in this form. But if you remember your fraction exponents and your negative exponents, remember that if we have some function, or even anything, in the denominator, we can bring it up to the top by making its exponent the opposite of what it was, so negative in this case. And then the 1/2 comes from the fact that the square root of p is the same thing as p to the 1/2 power. So we can rewrite this. The 100 is still in the numerator, it hasn't gone anywhere. And the variable component looks like p to the negative 1/2 power now. So this is actually a great place to be. Remember that we can ignore this 100 as a constant multiple, and really all the action is right here, because this is the piece we can use power rule on. So if we imagine pulling this 100 out and only having to think about it later on, the derivative of this is power rule. So the negative 1/2 exponent comes down, there it is, and then we reduce the exponent by 1. Negative 1/2 reduced by 1 is down even further negative to negative 3/2. This is more exemplary of the kind of work that I would hope that you would show, although I can imagine you skipping even more as you get comfortable with these rules. So the prior example, I pieced out all of this constant multiple and power rule subtraction and all that stuff, and this is more like what I would expect to see work on an exam. So at any rate though, again, notice that the derivative operator has gone away. The ddp is out of this last expression because we finally did take the derivative. We found the rate of change of p to the negative 1/2 power. So with a little bit of simplification, 100 times negative 1/2, we get negative 50, and then p to the negative 3/2. So now it's time for us to actually plug in this value. So if we take p equals 500 and plug it into our percentage rate of change, This is our big old expression. And d prime of 500 is something we can figure out. We just figured out d prime of p for any value. And d of 500 just goes back to the demand function we were given to begin with. So here's, just to track down all the pieces here, here's the 100 that was there from the beginning. D prime of 500 is the derivative expression we just figured out, but with a 500 in for p. So negative 50, there's our p-value, 500, to the negative 3 halves. And then finally we have, on bottom, the original function back again. So d of 500, that's just demand, which looked like 100 divided by the square root of p. So 100 divided by the square root of 500. And then through some convenient algebra, either just grabbing a calculator and doing this, or going through the delight that is simplifying fractional exponents, we get actually a pretty tidy number, negative 0.01. And as with regular derivative calculations, the interpretation piece is one of the most important facets. So what does this number actually mean? Well, we figured out a percentage rate of change. So this means that when we charge a price of 500, so we're reminding ourselves that 500 is our input value here. And what we're saying is, we're saying something about how demand is dropping. And it's not just that it's dropping by 0.1 million tons, it's dropping by 0.1%, because this is a percentage rate of change calculation. So 0.01% is because we actually went through this whole fraction process. So we're not getting an absolute measure of rate of change. We're getting a relative one, a percentage rate of change. So for every $1 per ton increase in unit price, we would expect the demand for rice to go down by about 0.1%. That's it for our relative rate of change. We'll come back in the next one for our final learning objective of the section.